Okay, good afternoon, everyone, again. And I'm Manas Upadhyay. I'm an assistant professor from LMS. And it is my pleasure to welcome Eric Maire today for the LMS seminar. So Eric Maire is from the MatéIS lab in Institut National des Sciences Appliquées de Lyon. He's a CNRS Research Director, DR1 at the MatéIS lab, and he is the director of the lab since January 2019. He completed his materials engineering studies in 1995 from INSA Lyon, and then he did a postdoc at McMaster University in Canada before coming back to France via CNRS at MatéIS in 1997. He has pioneered in-situ experiments in X-ray computed tomography, originally at synchrotrons and then more recently in laboratory tomographs. More generally, he focuses on material science, trying to understand the relationship between microstructural properties, working mainly on deformation and damage in metals, composites, and highly porous cellular materials. He has also worked on materials processing and developed a recent interest in materials for energy storage, for instance, lithium-ion batteries. He supervised about 20 doctoral theses and 10 postdocs. He spent a sabbatical year at Harvard University in 2010, and he was an invited professor for a month at the Tohoku University in 2015. He has authored and co-authored more than 250 articles in international journals and received more than 11,000 citations. And today he's going to talk to us about in-situ experiments in X-ray tomography. Eric, please, the floor is yours.
Thank you. I start my chronograph. Thank you, Manas, for the introduction. Thank you to the team at LMS for the invitation. So I will speak about in-situ experiments in X-ray tomography. There is a subtitle to this talk. It's exploring the interior of ordinary materials to improve their mechanical analysis. It's been a long time that I am using this technique, in-situ experiments in tomography. So I have many different type of examples, old examples, more recent examples. The reason why I focus today on what I call ordinary materials, is that these are the most recent examples, the most recent PhD studies that I have co-supervised. So, and also I think it's nice to look at some of these materials, ordinary materials, but using high level characterization methods. So, as said, my name is Eric. I work at MatéIS in Lyon. I am CNRS Research Director, and I am doing this type of studies since for 20 years already. But I don't work alone. I'm going to show today some work which is done in collaboration with my colleagues at INSA, Jérôme Adrien, Justine Papillon, Christophe Le Bourlot, Sylvain Dansette, Xavier Boulna. And I will mostly show results from the PhD thesis of Julie de Villard and Aurélien Sibélas. I will not have time, I think, to touch about the work of Victor. We'll see in the end. Okay, so as an outline, I will just introduce you briefly the method in something like 10 slides. And then I will illustrate the methods using recent examples of ordinary materials. What I mean by ordinary materials is materials that we use in very commonly in everyday life. Meaning, I'll speak about plasterboard, I'll speak about yarns, wires, and I'll speak about rubber, the rubber that we use to make the tires of the car. Just a quick check. Manas, is it okay for the beginning? Everybody can hear me? Okay.
At least I can hear you. I don't know. I suppose everyone is hearing you.
Okay, but you, okay, just feel free to stop me if something gets wrong, okay?
Yes, don't worry. Yeah, I'm here.
I sent an abstract, and I also said that maybe if I have time, I will give a bit of advertisement of what we are doing in the field of powder metallurgy. It's not exactly everyday life, but if I have time, I will keep you updated with the things that we do in terms of additive additive manufacturing at MatéIS, probably very quickly, very shortly. Okay, so let's go to the point. The first point is this general overview of the different available methods that we have to make 3D imaging in material science. On the left, you have destructive methods. These are very old methods that we've been using, which are mostly based on you take a picture of the polished surface of your sample, and then you remove one layer by subsequent polishing, and you make another image. This is called serial sectioning. It's very nice, very useful. It gives you, in the end, a 3D image of your microstructure. The problem is that it's destructive. So that's the reason why I will mostly speak today about the non-destructive methods, which are also existing. There are some methods based on reflection, emission, and scattering, which I will not speak about today. I will rather focus on the methods that are named transmission and rotation, because these are non-destructive, and this is the basics of X-ray tomography that I am using. But you can also do it with electrons or neutrons. And the principle of this transmission rotation method is explained in this slide. So this here is the sample that you want to image. This is the microstructure of one slice of your sample, the slice which is in the screen, in my screen now. You can also imagine that the sample is in 3 dimensions by thinking that you have similar slices above the screen and below the screen, okay? But if you understand what I explained to you for this slice, which is included in the screen, you will understand completely the method for a 3D case. So if you have a source of rays, for example, X-rays, that you send to your sample, if you have a detector behind your sample, you can record what we call the attenuation across the sample. Attenuation is very high when you have a lot of material, when you have very absorbent materials. So in this angle, you can obtain an attenuation profile of the X-rays by your slice. And this profile is summarized in a line here. And the principle of the method, rotation and the transmission, is exemplified here. Instead of one of these projection, if you acquire a high number of projection, you will obtain what you have on the right, which is called a sinogram for this slice, which is the set of different attenuation recording by your detector as a function of the angle. You see here the angle is changing. So if you are able to obtain a sinogram like this, you will be able to back project, to filter, back project, and Fourier transform your sinogram and magically reconstruct the image of the attenuation inside your slice, okay? So this is the principle of all these methods. It's non-destructive, it is quite fast. You just need to record some radiographs and you can obtain the image of your microstructure of your material. So now if you want to implement this method, what you need is what we call a tomograph here. For X-ray computed tomography, you need a tomograph. So on this slide, you have two different types of tomograph. You have the synchrotron tomographs. You recognize maybe here the Grenoble, Switzerland, Soleil in Paris, and the Japanese synchrotron. And since about 2005, you can also have very nice equipment in the laboratory. So this is an example of the MatéIS laboratory tomograph, but you can also find some other examples in École des Ponts, for example, or in the LMT. So all this is very, very close to the LMS. So when you obtain, when you are able to non-destructively obtain images of your sample, this very quickly calls for in-situ experiments, which I will explain later. So in-situ, I've been doing in-situ experiments since something like '93, when I was doing my PhD. I was using the gold grid printing method that was given to us by some people at the LMS, Thierry Breteau, Caldemaison, Borner. So I've been using these in-situ experiments in SEM for a very long time. It's very useful. It is still very useful for qualitative imaging. It's very useful for understanding the deformation mechanism at the surface of a material. But because it is limited to what can be seen at the surface, there is a limit of this method for quantification of the different microstructure and damage in materials. So this is why we have moved to non-destructive three-dimensional imaging, which gives you nearly the same as in-situ SEM, but this is going to be in-situ 3D imaging. So we've started this in '95. We have made tension in the beginning, and then we have done fatigue. My colleague Jean-Yves Buffière is still using the method a lot in collaboration with Eric Charkeluc from LMS to make these fatigue observation of cracks. You can change the temperature of the sample. You can increase the temperature during a tensile test. We can do compression, hydrostatic pressure, indentation. A lot of modalities are now available with this technique. But if you want to implement these modalities, you will need a rig, a machine that you incorporate in your tomograph, and that will allow you to stress, let's say, or to heat your sample. So here you have an example of different types of machines that we have built, rigs that we have built to make these experiments. Sorry about I speak twice here. So some of these rigs have to be sometimes it's very tricky. It's very tricky, for example, to have this machine rotate very quickly to make a high-speed acquisition. So we have been developing rigs for synchrotron and also rigs for laboratory. These are examples on this slide about for laboratory tomography. You can see some special device for high pressure, indentation, cooling, low temperature, or heating, high temperature, or simple tension. Okay, so to summarize the introduction, we have a lot of tools available. We can make in-situ tests, X-ray imaging at multiple scale, any type of simple mechanical loading, and we will obtain a qualitative observation of the microstructure in 3D, but we can also deform this microstructure and understand the deformation mechanisms. And because it's non-destructive and three-dimensional, it's very highly trustable. You can really trust the quantification that you make. And based on these images, you can also, because you have three-dimensional images, you can make 3D image processing, which will allow you to feed some subsequent analytical models, for example, or to feed numerical simulation, which are directly based on the images that you have obtained. And I will show you several examples of this type of approach. And because you have three-dimensional images, but also you have the evolution with time, you can use these observations to validate or to invalidate the models that you have developed. Especially, you can validate these models at very local scales, because if you have a series of three-dimensional volumes, you can use digital volume correlation to map the strain field and then
Eric? Eric? Can someone hear me?
Plasterboard. It's the PhD study of Julie de Villard. She has defended 6 months ago, something like this. And it's a study that was commissioned by Saint-Gobain Recherche. And Saint-Gobain Recherche is the biggest selling company in France of plasterboard, gypsum. This type of plasterboard that we see here, that we have a lot in our construction environment. So plasterboard, if some of you have already tried to carry one of these, you know that it's very heavy, and then you understand that it could be quite useful to obtain something which is a little bit lighter. So Saint-Gobain is trying to reduce the weight of these plasterboards by including bubbles in the standard plaster. So if you include air bubbles, you will obtain something which is light. The problem, it's going to be light, but it's also going to be less stiff, and especially what is a bit embarrassing, it's going to be less resistant to indentation. And indentation is one of the limiting properties for these materials, especially because of the way these plasterboard are fixed. You see here, you know probably here that here you have to screw something, and if your material does not resist to indentation, you have problems with screwing. So indentation is really the useful test to analyze, to limit the properties of the plasterboard. So gypsum, normally plaster, has different types of porosities. Normally it has two types of porosities. You have the porosity between the needles, which is called the microporosity, and you also have the porosity at a higher scale, what we call the mesopores. So if you look at these two images, this is the microstructure that you have in a standard plasterboard sample. What Saint-Gobain is doing is that they are blowing bubbles here, which gives you a third level of porosity, which we call the macropores. So the PhD of Julie was about finding the impact of these new large macropores on the indentation properties of the plaster, a very simple and everyday life material. So what we did is we applied the full procedure that I've been explaining to you before, which is we started with in-situ indentation tests. So we made indentation inside the tomograph. So this is the type of examples I will show you. We did it interrupted, which means that we load the sample, we displace the indent, and then we scan the sample, and then we displace the indent further and scan again. This is called interrupted in situ. We have 10 loading steps. Everyone is, between everyone, we move the indenter of something like 100 microns. So we have a 6mm diameter indent made of plastic to prevent the attenuation problems that sometimes you have in these X-ray method. The peculiarity also of the experiment that we have done here is that at the same time, on the same sample, we make two different scans for one single step. We make one scan with a 2 micron resolution and another scan with a 5 micron resolution. So instead of one scan, we do 2 scans. This is very easy to make in a laboratory tomograph. You just have to change here the distance between the sample and the detector. So if you go very close to the X-ray tube here, you will be able to have high resolution, for example, 2 micron images. If you move your sample a bit further towards the detector, you will be able to record a larger field of view, but less resolved second scan. So we record the force, displacement, and this is what we observe. So this is a side view. The indent is going down, And we can analyze, this is a low magnification, 5-micron resolution, and we can analyze the degradation of the plaster during the indentation. We can also visualize this test from another point of view. So now this is a slice in the plane, and the indenter is coming from the top, for example, and we can see the evolution of the microstructure in what we call a process zone or a damage zone below the indenter. And you can also see that there is very, very little amount of change outside of the process zone. So this was the low resolution image. You see here exactly the same test, but with the 2-micron resolution. And you can see that the 2-micron resolution allows us to see more details in the microstructure. To see what you see here is the mesoporosity that I was mentioning, and you can very clearly see how the macroporosity is changed during the indentation. You can also notice like these white spots here, which are dense impurities, which are always found in these plasters. So again, if you see it from the top or for the bottom of the indenter, you see again the same type of damage developing in the damage zone. So here, because we have this series of volumes, we could make digital volume correlation. And we use digital volume correlation for an image processing purpose, which means that we use the residual field obtained from the digital volume correlation that you can observe here. We use this to better determine the shape and the size of the process zone. So, sorry, if I do this again, this is a threshold on the residual field of the strain measurement by DVC. And it allows us to very clearly define the size and the shape of the process zone. So we've done this. I showed you one example, which was mostly in this plasterboard on the right, which is a lightweight plasterboard. And for comparison, we also have a second sample, and you can see that there is much less bubbles. There is much less macroporosity in this one. The density of the sample is much higher. This is what we call heavy plasterboard, and this one on the right is called lightweight plasterboard. So we have the two indentation curves recorded. Of course, the indentation curve for the heavy one is the force is higher for a given indentation depth. These two images we can compare, and we can analyze the difference between the damage collapse mechanism of these two different plasterboards separately. So again, I was mentioning that we use the residual to define this, which is the size and the shape of the process zone, and then we will use it to analyze the amount of gypsum which is displaced in these different zones. Because, so sorry about this, but it's just to exemplify the way we do the 3D image processing. We use this to mask this image and to quantify. This is the residual. This is the mask that we can calculate based using this, and then this is the mask that we apply to the sample to analyze what is happening only in the process zone. So we've used all these information first, to produce a very simple analytical model which allows us to predict the force, these indentation curves that we obtain, force as a function of the depth of the indent. So I will not describe fully what we are doing here, but just we use we use the indent, which is penetrating in the microstructure, and we use the initial image of the microstructure to calculate the possible value of the force. And sorry, I go very quickly in this example because this very simple analysis allows us to have a good agreement between the model and the experiment, just based on a simple information. What is the amount of material that you have in the process zone? We have also developed some more complex numerical models based on finite element procedure. So in this numerical procedure, what we want to do is to account for two levels of porosities. The micro porosity is too small. We cannot see it, but we can account for the macro porosity, which is the black circle that you have here. And we can also account for the mesoporosity, which is in gray here. And the way we do it is we change the properties of these elements here by considering the amount of porosity, of local porosity that we have in each of these elements. So we select this element, we calculate what is the volume fraction of gray in this element, and depending on the local volume fraction of gray in every element of the mesh, we change the properties. If you have a fully white element, the properties will be very high. If you have a lot of black or gray in the element, the properties will be strongly reduced. So Julie has made this type of analysis, and she has made some simulation of the indentation based on all these information, the initial microstructure, the properties of the microstructure very locally at the scale of every element in the mesh. And she was able to make this indentation. She was also able to compare, especially in the very beginning of damage, of deformation. You can see here what she observes in the beginning of the simulation, and this is very much similar to. Oops, sorry. If you look at the beginning, the deformation is in the beginning. It's following the experimental. At some stage, we have to stop the calculation because when the deformation and damage is too important, then the calculation, of course, becomes not so easy. She has been doing, well, the question that you may ask is, what are the properties that you use for this plaster? So in the finite element method, we have been very pragmatic. We have used Drucker-Prager behavior and Gerson behavior. These are two different damage models that can be a little bit questionable, but that were available in the finite element software, and that gave some useful information. We are very aware of the fact that this is not exactly perfect, but at least in a qualitative way, it gives a good estimation of so here you have a comparison of the size of the process zone in the finite element calculation compared to the size in the experiments. What we observe is the zone is much larger, is a bit larger in the calculation. You can see also that Julie has implemented 3 different kinds of behavior, Drucker-Prager, Gerson, but also she has changed the elastic properties. Here you have porous elasticity, and here you have linear elasticity. Okay, the last example extracted from the PhD of Julie is the comparison of the calculation that you have here with the residual that we see in the experiments. And again, this is only valid in the beginning of the experiment, because when you go at a too high deformation, the experiment, the simulation is not so good. But in the beginning, for the very first instant of indentation, the comparison is quite good. And this is quite good using the 3 different types of behavior that Julie has been using. Okay, so I spent a little bit of time on this example of plaster because everything is included in the example. You have DVC, you have image processing, you have in-situ experiments. So I will probably be a little bit faster for the 2 other examples. The first one is the study of the extracted from the PhD of Aurélien Sibélas, who has worked on the behavior of this type of objects. So a very common objects that we use in everyday life, and which is still not very well known from a mechanical point of view. I was very surprised when we started to make the literature review. There's not a lot of work, and the reason for the lack of this amount of work on these on these materials is that it's very difficult to observe the mechanical, the microstructure of these materials. So this was the PhD of Aurélien, and the PhD was co-supervised by me in MatéIS and also by Damien Durville, who is a specialist of numerical simulation of this type of objects. So this type of object, which is a high number of filaments that you pull, that you assemble together, and then you pull on these objects. This is what you find in strings, yarns, ropes, cables. A lot of different objects are made like this, and it's really fascinating the amount of possibilities that you can have to mix the different type of these yarns together, and the different type of mechanical properties that you can obtain depending on the initial conditions. What you see here is an example with a multi-yarn rope, which is composed of nylon in white here and aramid in yellow. So the behavior of aramid alone is like this. It's very stiff and it's quite fragile. The behavior of nylon is here. It's very soft, of course, because of the nature of the fibers. And if you mix the 2 together, you can obtain a hybrid behavior, which is in between. And there's a lot of different combination that you can imagine and produce with these different type of yarns. So it would be very useful to have a method to calculate the force, this type of curves, which are the force elongation, based on the knowledge of the properties of the different yarns that you put in the mix. So this was basically the idea of the PhD of Aurélien. So based on this idea, of course, we have applied the method, which is in-situ tensile test on these peculiar objects. So we had to adapt the grips. You see here, this is the rope, the yarn that we want to pull. The yarn has to go like this, and we put this yarn in a tensile machine, and then we analyze the initial state, and then we deform the cable, the yarn. So just like in the previous example, we obtain a very detailed observation of microstructure of the rope. We can reconstruct this microstructure in 3D. We can change the level along the wire, and we can add the different images together like this to scan a very long part of these ropes. And what is interesting with this type of image is that you can very easily analyze the trajectories of these different filaments. And the trajectories of these different filaments is exactly the information that was missing to obtain a very good prediction, analytical prediction of the force displacement curve. So this is the type of wires that we had. We had nylon fibers, PET fibers, and aramid fibers. We had mono yarns or multi yarns, 2, 3 different assemblies of yarns. So in theory, if you look at a single yarn, for example, in theory, the fibers should follow this type of trajectories. But it could also follow this type of trajectories like this. There are several models which make an assumption of the type of trajectories that you have in your yarn, and depending on the trajectory, you can obtain the angular distribution, which is here you have the angle of all these yarns, all these filaments that you have in the yarn, and this is the amount of fibers that you have oriented at this angle. And this distribution of segments of fibers as a function of the angle is the key information to be able to calculate the behavior. Because the tensile experiment is just a question of taking these angles and trying to bring them along the tensile axis. Okay, so these are the different assumptions for the trajectories, and these are the different angular distribution that would result from these different assumptions. And this is the reality. This is the real life. If you take one of these fiber, if you follow it, you will see this type of trajectory. So Aurélien was able to acquire a lot of trajectories and to calculate a lot of these distribution, experimental distribution of the angle, which then can be used to implement a model. So this is an example of the distribution for one single yarn, two different, a multiple yarn with two yarns, and a multiple yarn with 3 yarns. So you can see the shape of this distribution, and you can see that there are 3 different curves here, because the shape of this distribution depends on the twist of the initial cable that you can also change in the machines that you use to produce these yarns. So a lot of complex analysis of the trajectories and of the distributions. And here, this is a comparison of the experimental distribution with the different theoretical ones, where we were able to demonstrate that there is no existing model that allows to describe completely the distribution of angles. This is another analysis that can be very easily done. If you average the orientation that you have in a section of the yarn like this, you will obtain angles like this. Here, the color is proportional to the angle, and you can very clearly see that the fibers which are close to the axis of the yarn have very low values of the angle, whereas outside you have very high values. And also very interesting is this quite easy to anticipate. This is a little bit more difficult to calculate. What happens if you have 2 different yarns that you mix together? Here, the situation is completely changed. The angles are very high in the middle, and they tend to reduce outside. Okay, so all this as a summary to explain you that this is X-ray tomography with tensile tests is a very useful way of obtaining distribution orientation that then Aurélien has used to implement in a new analytical model. The model is based on an energy balance, I don't want to describe everything here. I just show you the ingredients. There is this here. There is this distribution of angle, which is very important. And also, of course, there is the tensile curve of the fiber alone. The property of the fiber is very important. Okay, so very quickly on the equations and move to the results. The first results is a bit, well, it's annoying for us. We've put a lot of effort to calculate complex angular distribution. And when we apply the model, we see that the average angle is enough to make a good prediction. Okay, this is a bit annoying for the time that we have spent on making this demonstration, but this demonstration had to be made. And now that we have demonstrated that the average angle is enough, then we can proceed and work and continue to work. Just as a summary of the result that Aurélien obtains, very satisfying results in very different types of configuration for nylon fibers, for aramid fibers. Here you see the comparison between experiment and modeling for different twists, again, for different initial twists, for single wires, for multiple wires. So the model that he has developed is very, very convenient and very useful. So one last word on this, the wires. We've been also doing some numerical simulation based on these observations using the multi-field software which is developed in École Centrale by Damien Durville. So I show you one animation. It was very difficult to fabricate the yarn, to produce the yarn. And the final solution that has been the most satisfactory was to really simulate the way the yarn is produced. So we've got a yarn like this, and now you can pull on the yarn using the numerical software. And you can see that the comparison between experimental and simulation is again very good. The advantage of the numerical simulation is more difficult to perform, but of course there are more detailed information about the local deformation in the fibers. So I see that I will probably have to skip this example because I see that I am at 41 minutes. It's just, again, it's Aurélien, after the PhD of Aurélien, because we were so happy with his work and he wanted to continue 1 year with us. So we have moved him to another subject. It's very different. It's the 3D deformation field under a spherical indentation of rubber. I will not detail this here. I will just show you briefly the results that we obtain. So same type of procedure. You have the rubber here. You push with a plastic indenter. This is the tensile curve, the compression curve that we record. And this is the microstructure of the rubber. It is full of little white spots, which are used to make a full DVC, digital volume correlation, calculation of the strain field in the material. And I just show you this illustration. This is the experimental strain field that we calculate with the test. And of course, we compare this stress field with what we can compute from a very simple numerical simulation made with axisymmetric elements. And this is the comparison of the experimental on the left and of the numerical observation. The comparison again is quite good. So, of course, what we intend to do is not simply to indent with a simple sphere. We also want to indent with a real material, with a real soil. And this is to simulate the interaction between a real soil like this and a rubber tire. And you probably understand for whom, which type of company it could be useful. Okay, I will very quickly go through my last part, 2 minutes. It's just, you cannot make a seminar these days without speaking a little bit about additive manufacturing. We also have a lot of collaboration with the people in LMS. So I just wanted briefly to summarize the research axis that we have in MatéIS in this field. So the first axis is we make a little bit of processing. In processing, what we do is we don't have yet, but we are in the process of buying a little atomization tower, which will allow us to produce small batches of powders with any type of composition, any type of metallic composition. This is something which has been accepted by the Rhône-Alpes region, and we are in the process of buying it. In terms of processing, we also do powder characterization. And for powder characterization, we use a lot X-ray tomography also, because we take, for example, we use X-ray tomography to analyze the granulometry of the powders and to count the number of powders which are hollow, for example. We also do, we don't have, in MatéIS, we don't have any selective laser melting machine. Rather than this, we use direct ink writing. We use this little method here, which allows us to produce this type of simple samples. But we also make some collaboration with some other partners, for example, in the group of Aude, for example, in Grenoble, the CIMAP laboratory. They send us the samples and we make in-situ tensile tests on these additive manufactured samples. And so I will skip this, but again, we use the same procedure, in-situ tensile test or in-situ compression test, to analyze the deformation inside the materials. So this I will skip, and this I will skip, and this also, sorry for going very quickly in the end. This is my conclusion. I tried to show you that with non-destructive 3D imaging at different scale, this calls directly for in-situ experiments that you can analyze post-process with digital volume correlation, that you can compare with image-based finite element method. And all this is a full procedure that can lead to new perspectives in material science and materials mechanics. So this was my final slide. I conclude, and I thank you for your attention.
Thank you very much, Eric, for this very nice talk. The floor is now open for questions. If there are questions,
I must say,
sorry.
No, I just wanted to comment. It's really a funny situation to have not to see the public changes a little bit the way you are doing the lectures. So it's really funny. Okay.
Okay, so we have a question already from Patrick. Patrick, please go ahead.
I don't see which company you know in the Rhône-Alpes region were interested in rubber, but I think I know the same. In your invitation test that you want to do on the soil, do you want to do a dynamic or a quasi-static? I mean, you will try to have a rough soil and indent on it?
Yes, it will never be dynamic enough to be at the time scale that all these people interested in soil versus rubber adhesion would like us to make the experiments. This is not possible. So this is going to be quasi-static loading.
Okay.
There is no procedure which is available to give us at the same time the good precision that we need to see the markers to be able to make the DVC experiments and sufficient time resolution.
Okay.
But still, from static and quasi-static studies of compression, and What we plan to do is compression and also compression and torsion.
Ah. Thank you.
Okay, we have another question from Kostas and then from the attendees. Let me see it. So Kostas, go ahead.
Hi, Rick. Thanks for the talk. Very nice talk. My question is about this tomography, etc. So we're able to study a number of problems. We see this. Then models can be developed or improved based on these studies. Can these techniques be used to propose solutions? Like, how would you interact back with a model that works or doesn't work? And then how would you go back to the tomographer to propose? For example, you started the talk saying that you want to screw something in this plasterboard, but then when you do the experiment, the model seems to produce a much larger zone. Mm-hmm. So what is the process? How do you go to the end and give a solution? Because one thing is to study, and then the second thing is to go back and give a response. I mean, how can you use the tools provided? How can you compare, let's say, the model and probe the models to a better detail to see why the model doesn't work? And you understand my question? Maybe it was not very clear.
Yes, I understand your question. So to make identification of, let's say, of behavior, it's much easier to have simple analytical models and go fast, okay? And here there is no real need for detailed observation of the microstructure and dialogue between the heavy finite element calculation that you can make based on the image and the detail of the microstructures. But so if it's for model validation, or I don't think it's the right tool. I think it's a good tool for microstructure optimization, because the global behavior that you calculate very often is not very accurate. But what is interesting in this simulation is to observe the kinematics of the deformation, the regions which are highly loaded locally in the microstructure. So to summarize my point, and I hope it's a good answer to your question, it's very good for local comparison, and it's not the good tool for global comparison. For global comparison, it's much easier and much clever to use a simple analytical model. But for local comparison, damage optimization of the microstructure of a material to resist damage. It's very difficult to do it on a global manner. But if you are able in the microstructure to analyze the local spots where the stresses are very high and suggest some ways of removing these spots, I think it's the way to tackle the problem. And there is another answer to your question, is the computers are going faster and faster, okay? So it's already possible today to have fast comparisons like this at the local scale. And the comparisons at the local scale, again, in my opinion, are going to be a little bit more rich than the comparisons that we can make at the global scale. I don't know, Manas, Kostas, if I answered correctly to your question.
Yes. No, I mean, yes, to a big extent. My question is, what if now the models that you use don't work, or they do not work well? How can you inform the models? Can you give more information on what part of the model needs to be from the tomograph?
Yeah, I'm sure.
Right?
Well,
to what extent you can, you see what I'm saying? Because, for example, in this plasterboard, you see that the zones that you find with the model are much larger. And what is the mechanism that I mean, how easy it is from these tomographic images, because I'm sure they contain huge amount of information. How easy it is to inform which part of the model needs to be improved?
Well, a simple answer is today, this is like this. This is by nose. You see that your region is too large, then you will change a parameter in your model, which you know is going to reduce the size. But I'm sure that very soon there will be some image-based learning that will allow you to know which is the better parameter to change in your model to bring your results closer to the local field. Again, I think it's more rich because it's local.
Yes. Okay. Thanks.
Okay, Eric. So now we have a question from the attendees and then from Aude and Andre. So I'll go to the attendees now. Okay.
Yeah, sure.
We have Larbi Siad. Larbi, you can unmute yourself now and ask your question, please. You need to unmute first before asking your question.
You want me to,
or I can do it for you.
Do you want me to stop sharing the screen maybe, or?
No, it's fine for you. It's completely fine. Okay, Larbi, I'm unmuting you. Please ask your question. Yes, please. Can you ask your question? Do you hear something, Eric? Or
no? I'm listening, and during the I hear something.
Yes, Larbi, can you repeat it, please?
I don't hear anything.
Yeah, me neither. Okay, Aude, can you go ahead and ask a question, and we'll come back to Larbi after.
Yes, thank you, Eric, for a very nice talk. I was a bit wondering, but the question you had from Kostas is a bit similar. And I had asked it before he actually asked it. So this is why it's probably going to be redundant. But in this plaster story, can we really use the tomography or the simulation to optimize the pore distribution? Do you think this would be something really interesting there?
Oh yes, I think so. We had no time to do it, but it's been a long time that I would like to produce something which makes a dialogue between the images and the local fields that you can simulate using the images. Because I'm sure that this is maybe an old way, and let's say not very modern way of doing the things, but I think that you can change your image based on the information of the local stress. And then you can use a given microstructure and you can polish it a little bit to propose or to suggest a new microstructure which will have reduced amount of stresses and maybe same amount of same density, or maybe reduced density and same strength.
Okay, yeah, interesting. You should probably be able to use the simulation to see if also it's possible to do some optimization and then try to produce the material. There should be a back and forth maybe between the experiments and the simulation.
Yes. This is an old idea that I still didn't find time and student and money to test it. But
it's the problem of the 3-year PhD in France, you see.
I know.
You don't have time to do optimization at the end. Okay, thank you very much for a nice talk. Thank you.
Okay, so in the meantime, we have 5 raised hands and questions. Andre, can you go ahead, and then we will go to the audience again, please.
So I'll try to be short. So thank you, Eric, for the seminar. Very nice. So my question was the following. So actually we are measuring density with the tomography. And from this density, we want to go to texture, to material and a texture. So how do you arrive to get the angles of the yarn from one cut to the next cut?
Okay, we've done it many times. I must have, I try to find it. I think it's explained somewhere. So, as you anticipate, here, I think it's here. You see here, as you anticipate, the whole point is to find the center of the fibers in one slice.
Okay.
And it's the only example in image processing where I work on slices. Normally, I work on volumes because normally it's better using volumes. But in this peculiar case of fibers which are cut by a plane, it's better to work in slices. And then there is a procedure. You do this
so you try to track the slices, how they go up.
Track the slices.
Okay. Can you then use this information to get something about the internal friction which would exist between the fibers using a type of model? So making the dialogue Costas and Odd were talking about before?
Well, yeah, this is not something that we've tried. We know that there is a question of dissipation.
Yes.
By fiber sliding, except that in this very special case, the fiber sliding is not very important. Okay. Because all the fibers are nearly parallel and you pull on the fibers. There is a little bit of sliding, but much less than if you have a wool, for example. If you have fibers in every direction, if you have contacts like this, then friction is very is dominant on the behavior. But if all your fibers are like this and you pull like this, so this is the reasons why we didn't try to calculate or to simulate the friction.
Okay, thank you.
Okay,
thank you again very much for the seminar.
Thank you, Andre.
Okay, so now we will go to the audience again. We will give one more chance to Larbi to ask the question. Larbi, can you? I have given you the possibility to speak now. Please, can you ask your question by unmuting yourself first? Larbi, if you do not, okay, we will come back to you later. I'm giving now the chance to Abder Rahman Ayadi to ask their question. Abder Rahman, can you unmute yourself and ask the question?
Yes, hello, do you hear me?
Yes, I hear you.
Okay, thank you very much for this presentation. Actually, my question will be more technical. It's regarding the foam gypsum. The first question is how to choose or to adapt the voxel size if there is a need to perform DVC on porous materials according to the pore size.
Oh, okay.
So possible to elaborate on this?
Oh, yeah, sure. So
and the second question, to unmute myself later, is, for example, the choice of the number of steps to be able to perform DVC also in this indentation test. And thank you.
So both, in principle, you could probably anticipate in a clever way. The approach that we've used is for voxel size, we have made the experiment at two different kinds of voxel size. The same experiment, the same step at two different voxel sizes to obtain either a very detailed observation like this or a less detailed like the previous. And the step that we use, the step that you see here, what is the best step? I would say the best step is the longest step that allows you to make to perform the correlation.
Maybe not the best step, but the number of steps, discretization of the entire test list.
Well, the number doesn't matter, I think.
Okay.
It only depends on what is the maximal depth that you want to reach. What is more important is the distance between each step, because this is controlling your capacity to manage to make the correlation after the test. And this is the reason why we have chosen such a moderate penetration depth, only 100 microns that you see here. Because if you go too fast, too quick, and then you lose completely the software that makes the correlation, and it's difficult.
Great, thank you.
Thank you for your question.
Okay, so the next question is from Loic Sal. I'll give you the chance to talk now. Loic, please go ahead and ask your question after unmuting yourself.
Hi, can you hear me?
Yes.
Great. Yes, Loic Sal from Imperial College. I have a question about the technique, if it can be used for contact measurement, and especially the interaction at the level of roughness.
Yes, we will start a project like this with people from a neighboring lab, which is just close to my home office. So this is my home, this is my office, and there is the LTDS lab very close to here. And we have a project starting. So yes, it can be used to measure surfaces. The interest is that you can do this surface measurement in an opaque material. This type of surface measurement it's possible to do it on transparent material normally. And here we will do it in opaque material.
Can I ask another question?
Yes.
Sure.
It's related to that. It's related to the things that you said, you know, about dynamic and quasi-static. For contact, if you have slip, do you think you will be able to track the front slip? You know, the waves that go into the material because of slip?
Well, I don't think that we have for contact, you also have to have very high resolution to be able to resolve the contact. If you have very high resolution, spatial resolution, you will have a very low temporal resolution, and this will not be able for enough for stick slip.
Okay, thank you.
But you can always manage. You can always. People are doing a lot of improvement on the temporal resolution, but for the standard procedures that we have today, I think it's still not enough. And if you are at Imperial, can you say hello to Florian Bouville for me?
Okay. And are you okay if I contact you, because we are in the process to set up a project where we will use the ultrasound technique. So it will be nice if we can compare with your technique.
Yes, sure.
Okay, great.
Sure.
Okay, we have to move on. We have 6 more minutes before the end of the talk. So I will disconnect Loic. And by the way, Eric, Maureen Montagne says hi.
So, hi, Maureen.
She has left now.
Okay, very nice.
Yes, there is a question from Dana Daneshwar in the question and answer session. What type of FEM software do you usually use for mechanical characterization, especially for the pores in plaster? And is it possible to introduce some research groups doing this X-ray micro-CT for concrete mixtures?
So we use Abacus for because just by this is the first one I used, and now we continue to use it. We have it at INSA, but it's a mesh that you can export on any type of software. So it works with Zebulon, it works with many different types of softwares. Groups working on, well, of course, my good friend Michel Borner at École des Ponts. There is a group in National Institute of Health in America. Professor Garboxy is using it quite a lot. Concrete is not exactly my field of expertise, so maybe I'm sure I miss a lot. But oh, so yes, there are people in Grenoble, of course, in the Trois Essers laboratory, which are doing quite a lot of these also. I don't know if it's enough, but
I think that's good, yeah. Thanks. So there is another question from Jinbo Bai. Is Tomo suitable for in-situ monitoring of deformation? Fast enough to record the data? How long it takes to record an image?
Well, how long? It goes from a fraction of seconds, very quickly, to the standard answer to this question is something like 5 minutes. Normally, a good quality image, it takes you 5 minutes on a standard procedure to acquire it. If you are ready to sacrifice a little bit the quality of your image, you can probably go down to hundreds of seconds. I mean, 100 images, tomography images every second. The fastest I did with this rotation, high-speed rotation tensile machine was 20 acquisition during 1 second. But people are doing better and better. Everybody is pushing to increase the speed.
Okay, we have a few more questions, but we have only 3 minutes left. So the next up is Ali Ruwan. I will allow you to talk. Now you can unmute yourself and ask your question, please.
Hello, do you hear me?
Yeah, I hear you.
Hello, thank you for your presentation. My name is Ali Ruwan from Institut Toulouse. I have a question concerning the meshing of the microstructure of the Plasterboard. As you said in the beginning of the presentation, when dealing with the plaster, there are air bubbles, and my question is how accurate the mechanical assumption that we give for the mechanical model. Do you consider the air bubbles as do you consider mechanical properties for the air bubbles, or
no? As you can see, yeah, as you can see here, the air bubbles, they are not meshed, so they are like air. We don't. But again, you have to remember that all this is porous. So the air bubbles cannot contain air that cannot flow away from the air bubble. So it's really, the air bubble is really like a complete void.
Okay.
With no mechanical properties.
Okay.
Okay. We have time for one last question from Nagasai Meghna Rani Kauta. I will allow you to talk. Please go ahead and unmute yourself and ask your question.
Yeah. Hi. Thank you for the presentation. So my question is that, are there any limitations of size for the specimens that are used in a mechanical test with this type of technique?
Well, thank you. Very good question. The size limitation is related to the transmission of the X-rays. So if your sample is very absorbent, you cannot use a very big sample, because all the X-rays are going to be absorbed inside your sample, and there will be no X-rays outside your sample. So no X-rays behind the sample means no projection capabilities. So in this case, if your sample is very absorbent, like steel, concrete, you will have to reduce the size like this. And this way, you will have enough X-rays outside your sample, and you will be able to make an image.
Okay, thank you.
I don't know.
Okay, one very last question from Maire Azouzi. Maire, go ahead and unmute yourself and ask your question, please.
Good morning. Can you hear me?
Yes.
So Maire Azouzi from ITEM University of France. First of all, thanks for the presentation. And my question is about the lattice structures produced by additive manufacturing. Can the DVC technique give good correlation with this type of structures under compression tests?
Well, I think the answer is yes. Although, so we have tried a little bit DVC with lattice like this, if this is what you mean.
Yeah.
This is a lattice structure which is made by EBM in Grenoble, and we've been able to apply DVT with this, and it works. You have to adapt the size of the elements, but so the answer is yes, it works. It would be better. It would be better to be able to add some markers here, not connected in the middle of the void here. And I think it's possible if you put a gel which has no mechanical properties, which is full of markers that you will be able to track. I'm sure you will even improve the quality of your correlation.
Yes, thanks.
Thank you, Eric, again. Thank you very much for this very nice talk. And we had an attendance of 150 people during the talk. So that's really nice. And you gave an excellent talk. And I think that shows in the questions that were asked.